Very, very good morning to all of you, students. Today we are going to talk about potential energy, gravitational potential energy. So we have talked about kinetic energy and all. The expression we have derived yesterday. Kinetic energy is still half mv square, I have said. And also I said the kinetic energy depends on mass of the body and also the velocity of the body. Many things we have proved yesterday. And we have explained what is called the work energy theorem in this topic. Work energy theorem means the work done by a force is equal to change in kinetic energy of the body. All these things we have discussed. Today I am going to talk about gravitational potential energy. Gravitational potential energy is the stored form of energy. When a body is taken uh, at a certain height above the surface of the earth, we have to do some work and on the body to lift it to a certain height above the surface of the earth. And the work done by us is stored in the form of an energy. This is called potential energy. Potential energy is always a stored form of energy, right? Suppose that a body of having a certain weight, to lift it to a certain height, we have to apply a force that is against the gravity force. Gravity force is weight of the body. So weight of the body is most of the time written as equal to weight. Weight is equal to mg. Suppose a body is taken from the ground level to another level to a height h. What is mass of the body? Mass of the body is m. Weight of the body is acting vertically downwards. We lift the body to this much height above the surface of the earth. We have to apply a force that is equal to the gravity force. The body can be taken slowly without any acceleration to this point. The body has moved through a height h. So in this case, what is the force applied? Force applied by you to lift the body, F is equal to mg. F is equal to actually force is equal to weight, weight is equal to m. For what is the displacement of the body? Displacement is equal to h. Therefore, W is equal to F into displacement, F into S. So displacement S is equal to h. In this case, F is equal to mg, mg and S is equal to h. We will get this is equal to mgh. Whatever amount of work done on the body by you is stored in the form of potential energy. So at this particular position, above the ground, this body possesses an energy is equal to mgh. This is a stored form of energy. Am I correct? So we are talking about a gravity force. Gravity force means it is a gravitational potential energy. In gravitational potential energy, we have to apply a force is equal to gravity force. Now we will see something about what is called conservative and non-conservative forces. That is the next topic we are going to study now. Conservative and non-conservative force. Conservative and what? Non-conservative. Non-conservative force. So conservative force is a force, the work done by that when applied to a body does not depend on the path followed by the body. That is what is called conservative force. So force is doing a work and the body is moving, body is displaced. In any path it can move through, but the work done will be always same. So conservative force is a force. Work done by that force does not depend on the path followed by the body. It is independent of the path followed by the body. Then it is called a conservative force. One more thing. So work done by the conservative force to take the body around in a closed path is always equal to zero. Work done by the conservative force to a closed path. Suppose a body is taken from the initial position to so many positions and it is coming back to the initial position, then work done by the conservative force is equal to zero. So one thing I said, the conservative force is the work done in which the body can move through any path. That means work done by a conservative force is not depending on the path followed by the body. And also second point, what I said, when you take a body in a closed path, then the work done by the conservative force is always equal to zero. So for example, what I'm talking about is now an explanation. I'm going to do it. Suppose an object is placed here and this object is taken to this level. This position it is taken to using this path. You are taking this path. This position is A and this position is B. It can be taken to another path like this also. It can be taken. This is path number 1, and this the another path means this way also it can be taken. So from position A to this point and again to this position it can be taken. And this is 2 and this is 3, etc. Right? This is 1. This body is on the ground level. This is ground level. This is the ground level to height h. The body is lifted through many paths. Right? Surface of the earth, and the body is lifted to this height above the surface of the h. Then that can be done using this path, or using this path. In all these cases, the height attained of the body is equal to h only. Therefore, at this position, above the surface of the earth, the energy stored in the body is equal to only mgh. Whether it is through this path or to this part or to this or through this path, the energy possessed is always the same. So we have lifted the body to this position. Now it has energy stored in it is equal to mgh only. Mgh only. This also mgh. This also mgh. This also mgh. Now, suppose the body is brought back to the initial position, right? Brought back to the initial position. Suppose it is taken to this position and it is coming to this position. That means it is taking a round. So this through this path it goes and again comes to this and coming to the initial position. It is making a round. Then the work done by the force is equal to always 0. Because for taking the body, we are using our energy to lift the body to that is what is minus mgh. And when it is taken down, the gravity force is doing the work, that is equal to plus mgh. Therefore, minus mgh plus mgh is always equal to 0. That is why I said the work done by a conservative force to take a body in a closed path is always equal to 0. So conservative force is that force that does not depend on the path followed by the body. So gravitational force is a conservative force, we can say. Electrostatic force is a conservative force, we can say. Magnetostatic force is a conservative force, we can say. So all these are the best examples of conservative forces, right? Electrostatic force, and also spring force is also a conservative force. Right? Spring force means that is a variable force. When a spring is compressed or elongated, the force created at different conditions within the spring is what is called a conservative force. Spring force is a conservative force. Then what I said, gravitational force is a conservative force. Electrostatic force is a conservative force, because work done by all these forces does not depend on the path followed by the body. And also, work done by these forces to take the body in a closed path is always equal to 0. As I said, to lift a body, we have to expend our own energy, can be taken as equal to minus mgh. When it is dropped from the same point to the initial position, that energy is utilized by that. Right? Its energy is totally lost. So from a height, when a body is dropped, its potential energy stored in the body is utilized in coming back to its initial position. Now, when it comes back to the original ground level position, the energy is equal to 0. That is minus mgh plus mgh is equal to 0. This is conservative force. Non-conservative force is a force in which the work done by the force depends on the path followed by the body, right? And also we cannot say that in a closed path, when the body is taken, the total energy is not equal to 0, right? For example, if an object is passed on the surface of the table, we have to do some work, right? But to take the body back to its origin, again we have to do some work. That means the total amount of work done is not equal to 0, but total amount of work is equal to ongoing work done, and also coming back also we have to do some work. So that is never equal to 0. In this case, we can say that the work done by a non-conservative force is depending on the path through which the body is moving. So conservative force means that does not depend on the path of rotatability. But in non-conservative force, the work done by the force depends on the path of rotatability. And also to take the body in a closed path, the total amount of work done is not at all equal to 0. So this is the difference, right? Okay. So non-conservative forces, also the frictional force is a non-conservative force. Frictional force means, as I said, that now a body is when it is passed on the surface of the table, in both the conditions, taking to the initial position to final position, we have to do some work. Then final position, initial position back, then also we have to do some work. Total energy is not going to be equal to 0. So this is what is called what is called conservative and non-conservative forces. I have said clearly. Next is elastic potential energy. Potential energy is continued. We are actually talking about potential energy only. First, I talked about gravitational potential energy. Now, I am going to talk about what is called elastic potential energy. Elastic potential energy is the energy possessed by the shape, that is a configuration of a body. For example, a spring is when compressed or elongated, then work has to be done. A spring of certain length is there, up to here, right? It is low now. Now, suppose that the spring has to be made up to this much. We have to do some force. One point is kept fixed, and the other point we have to do some force. Then only this can be compressed. Am I correct? So for compressing the spring, we have to do some external work, and that work done is stored in the form of potential energy. That energy is what is called elastic potential energy of a spring. Even for a string also, string means a wire, a hard wire also, when extended or when it compressed, the energy will be stored in it. That is called elastic potential energy. So in the most of the conditions we explain you, we take the case of a spring only. A spring is extended, or it is, suppose this is the original length of spring, and now it is extended up to this much by the application of a force. By the application, when a force is applied, you see there is a pulling force which is created within the spring that will try to maintain or restore the shape of the spring. That is called restoring force. When we apply a pulling force for extension of the spring, there is a force which is